In this video, we will be discussing the concept of enthalpy of formation and using some enthalpy of formation values to determine the enthalpy for a reaction. Now, in a previous video, we had been talking about Hess's law and using the fact that enthalpy is a state function, which means it only matters where you start with and where you end. So you can actually take multiple different reactions that you know the enthalpy of reaction for, and if you can rearrange them in such a way to sum up to a new reaction that you're interested in, you can then add their enthalpy of reaction values together and come up with the enthalpy for the reaction that you haven't done. So whenever we use enthalpies, we are considering a change in enthalpy, not the absolute value. So it's the difference between where we're starting with and where we are ending with, right? Because enthalpy is a state function, it only matters where you start and where you end. And so we can only be ever considering a change because we need both a starting point and an ending point. Now there are a couple ways that we could conceptually think of using enthalpy values in some sort of a table to predict new enthalpy of reactions. One would be to list the enthalpy of reaction values for every single reaction that has ever been done, and then it would be up to the user to select reactions such that when you add them together, you get the reaction that you're interested in. This would be very inefficient, very labor intensive in order to figure out which reactions you're going to need to be able to add together to get the reaction you want. A different method would be using the fact that enthalpy is a state function to its greatest advantage, and that would be use a common reference state. So once we know the difference between that reference state and one of the components, we can have everything theoretically go from your starting material to the reference state and then back to your products, right? Because it only matters where you start with and where you end. So if they go through an intermediate reference state, you would end up with the same value. This second form is what we use when we're doing the enthalpy of formation. So the enthalpy of formation is derived from the change in enthalpy for the reaction that forms the molecule of interest from its elemental components in their most stable, naturally occurring forms. So the reference state is the element constituents in their most stable elemental naturally occurring form. So that would be hydrogen as H2, carbon in the form of graphite, oxygen as O2 in the gas phase, right? So their most stable naturally occurring form. So what we can visualize this as is taking our reactants, breaking them up into their components, and then reforming them into our products. So what we are calculating when we are doing a reaction is essentially the difference in energies between the reactants and the products. We are looking at all the intermolecular forces holding our reactants together, as well as the bonds holding our reactants together, and the attractive and repulsive forces of the products and the bonds holding our products together. Because enthalpy is a state function that is path independent, we can therefore describe a theoretical path to aid in our conceptual understanding of going from the reactants to the products. That is what we will be doing with the enthalpy of formation. We will be using a reference state where each one of these that represents the elements that make up our reactants and our products. This is the elements in their most stable elemental form. Now, because we're talking about reference sets, we need to specify very clearly the concentrations, the pressures, and generally the temperature. So the enthalpy of formation for elements in their most stable naturally occurring form is defined as having an enthalpy of formation value of 0. Because what you're looking at is the amount of energy that it takes to make what you are looking at from the elements in their most stable elemental form. So your starting point is the elements in their most stable elemental form, and your ending point is the thing that you are interested in. So if, for example, you're looking at hydrogen, H2, which is hydrogen's most stable naturally occurring form, the amount of energy that it takes to make hydrogen from hydrogen would be 0. Your starting point and ending point are the exact same. So what you'll find is that if you're looking in tables of enthalpy of formation values, either the elements in their most stable elemental form will be missing from the table, or they will have a value of 0. The reason that they would be missing from the table is because if it's the element in its most stable elemental form, everyone should know that the value is 0. However, in some tables it will explicitly say that it is 0, but not all will have it there. Now this superscript not means that you're working under standard state and conditions. Technically, there is no defined temperature for standard state. This is different from our standard temperature and pressure and our standard ambient temperature and pressure that we talked about when we were looking at ideal gases. However, generally, a value of 298.15 Kelvin is used, which is 25 degrees Celsius. But technically, standard state and conditions does not have a defined temperature value. So anytime you're looking at these values in a table, you need to make sure that you look to see what temperature that everything was done at. The pressure for your components will be 1 bar or 10 to the 5th pascals, which is the same thing. Now this changed from what we had in 1982 and before. Prior to 1982, the standard state was 1 atmosphere of pressure, but the International Union of Pure and Applied Chemistry changed our reference value to be consistent with all the SI units, changing it from 1 atmosphere to 1 bar or 10 to the 5th pascals. That change occurred in 1982. However, a lot of tabulated values still use 1 atmosphere. So you have to be careful when you're looking at the values to make sure that the conditions that the values are listed under are the same as the ones that you are intending to use. The concentrations for all components that would be listed as aqueous solutions will be 1 mole per liter is the standard state. So some of our examples of enthalpy of formation reference states would be carbon solid in the form of graphite. That is more stable than diamond. Hydrogen is going to be H2 as a gas. Sulfur would be S8, which is this rhombic crown-like structure. However, it was normally just listed as S, where it's technically the standard state divided by 8, but 0 divided by 8 is still 0, so it's perfectly okay. So the standard state for sulfur is this S8 circular crown-like structure. Now, once we have the values tabulated, we can use them to predict our enthalpy of reaction values using the enthalpy of formation. The way we would do that is we take our sum of our enthalpy of formation for our products minus the sum of the enthalpy of formation of our reactants. Essentially, we are taking the amount of energy that it takes to form our reactants, going in the reverse direction back to the elements in their most stable elemental form, taking those molecules in the most stable elemental form and recombining them into our products, right? Now that will give us a conceptual path that leads from our reactants to our products. And by taking the sum of your products minus the sum of your reactants to come up with your enthalpy of reaction, that will give us a valid enthalpy of reaction and a valid pathway for going from the reactants to the products. Let's now look at this in practice. So let's say we're interested in the combustion of ethanol, which would be C2H5OH, as a liquid reacting with 3 oxygen, 3 O2, in the gas phase, going to 2 carbon dioxide molecules in the gas phase and water as a liquid. And let's say we have a table that we've looked up here. This is our table of values. So what we'll need to do is figure out which one of the values from the table we're going to want to use. Now you'll notice that there are some extra values, or one extra value in here, and this is to simulate one of the things that you need to be careful with, right? So water we can have it either in the gas phase or the liquid phase in a table. This is fairly common. Some other things you might find in various phases. You got to make sure that when you're grabbing the values that you grab the one that corresponds to what you're actually interested in. The reason for that is if we're looking at water in the liquid phase, in order to form that, the molecules actually come together and they stabilize through strong intermolecular forces, which is why the value for water listed here is a lower energy. It is more stable than the value for water as a gas. Right? So when we are plugging these values in and trying to come up with our overall enthalpy of reaction, we have to make sure that we're using the correct value, the value for water, not the value for water as a gas. So we're going to use our equation that is the change in enthalpy of reaction is equal to the sum of the change in enthalpy of formation for our products minus the sum of the change in enthalpy of formation for our reactants. So writing this out, filling in our values, our change in enthalpy of reaction is equal, and now we can write out all of our values for our products. Right? So we have two sets of the change in enthalpy of formation for carbon dioxide. So this is 4CO2 as a gas plus 3 times the value for water. 3 times the change in enthalpy of formation for water as a liquid. Okay, that is all of our products minus the sum of our enthalpy of formations for our reactants. So this would be 1 times the change in enthalpy of formation for C2H5OH as a liquid plus 3 times the change in enthalpy of formation of O2 as a gas. And we'll take that and plug it in right there. Okay, so entering in our values, change in enthalpy of our reaction would be equal to 2 times negative 393.509, and that's kilojoules per mole, plus 3 times our value for the enthalpy of formation of water as a liquid. So that would be this value right here. So that's minus 285.830, also kilojoules per mole, minus the sum of our values for our reactants. So 1 times negative 277.0 plus 3 times, now our oxygen here, O2 as a gas, is the most stable elemental form for oxygen. If you look at the table here, oxygen does not appear, and that's because oxygen is the most stable elemental form for oxygen. And so the value here is going to be 0. If we plug this all into our calculator, we get an enthalpy of reaction value that is equal to negative 1367.508. In terms of our significant figures, this is all addition subtraction, and so it would be the value that has the least number of decimal places, which is the value for the ethanol. So we would cut it here. The units are kilojoules per mole of the reaction. And so our end answer would be negative 1367.5 kilojoules per mole of the reaction. Now, another way of coming up with our enthalpy of reaction values, and this would be typically used for new molecules. So if you go into like an organic lab and you synthesize something that is brand new, you typically, well, if you're synthesizing something that's brand new, you're not going to be able to find it in a set of tabulated values for the enthalpy of formation. So the way that we can determine enthalpy of reactions, and a sort of a quick and dirty way of doing it, if you don't have an extended table of enthalpy of formation values, is we can look at the amount of energy that it takes to break apart all the bonds, essentially atomizing all of our components, putting them into the individual atoms in the gas phase, and then recombining them. The general process is called the atomization energy, which is similar to the enthalpy of formation, except the enthalpy of formation values are referenced to the most stable elemental form, which is often a molecule. So like oxygen is O2, is the most stable elemental form. For these, what we're essentially doing is looking at all the energy that it takes to break all the chemical bonds and the energy that we get back from forming the new chemical bonds. So our general equation for the enthalpy of reaction would be our enthalpy of reaction is equal to the sum of the bonds broken minus the sum of the bonds formed, where these values here are listed as the amount of energy that is released when the bonds are formed. So putting this problem into action, our table here is actually a shortened version from the previous one, where we've taken out a bunch of data that we won't be needing. There is still some data that we don't actually need, but this is a simplified version of the previous table. So the way that this works is you need to know what your molecules look like so you can count up the total number of bonds. So the first thing you would do with this process is write out the Lewis dot structure for each one of your components. So for ethanol, that would be carbon bound to carbon. Each one of those is bound to a bunch of hydrogen. This is bound to an oxygen, that's bound to a hydrogen. O2 would be oxygen double bound to oxygen. I'm going to leave out the lone pair of electrons because for this, what we're really interested in is the number of bonds, right? So while we could fill this all out and include the number of lone pair of electrons, we don't actually need that particular amount of information in order to do what we're about to do. So we will just leave it out. Carbon dioxide would be oxygen double bound to carbon, double bound to oxygen. And then water would be hydrogen, oxygen, hydrogen. Okay, so our equation was the enthalpy of reaction is equal to the sum of the bonds broken. I'm going to put BB for bonds broken minus the sum of the bonds formed. Okay, so what we need to do is write out all the different bonds that are broken and all the different bonds that are formed. So in our ethanol, so essentially the bonds that are being broken are the bonds in our reactants. The bonds that are being formed are the bonds in our products. So our change in enthalpy of reaction would be equal to, so summing up all our bonds broken, we have one carbon-carbon bond. So we grab our value for carbon-carbon bond. So that would be, well, let's write out our bonds. One carbon-carbon single bond. We have 5 carbon-hydrogen bonds. We have, in our ethanol, we have 1 carbon-oxygen bond, and we have 1 oxygen-hydrogen bond. Okay, we will add to this our oxygen-oxygen double bond. So we have 3 sets of O double bonded to O. Okay, that is all the bonds that are broken. we subtract off the bonds that are formed. We have 2 carbon-oxygen double bonds per carbon dioxide, and we have 2 of those. So we have a total of 4 sets of carbon-oxygen double bonds. Plus, in our water, we have 2 oxygen-hydrogen bonds, and we have 3 waters, so that would be 6 sets of oxygen-hydrogen bonds. Okay, so we can now grab our values, or figure out where all of our values are in the table. We have our carbon-carbon single bond, we have our carbon-hydrogen bond, we have a carbon-oxygen bond, we have a carbon-oxygen double bond, but that is coming from CO2. So you see here, there is a very particular value if we're looking at CO2. We have our oxygen from the O2, and then we have our OH. Okay, so plugging all these values in, that would be 1 times carbon-carbon single bond, so that's 347, plus 5 times our value for a carbon-hydrogen bond, 413, plus 1 times our carbon-oxygen bond, which is 358, plus 1 times our oxygen-hydrogen bond, which is 467, plus 3 times our oxygen double bond. So that would be, we will continue over here, plus 3 times 498. Okay, that is the sum of the bonds that are broken, coming all from our reactants. We then subtract the bonds being formed, which are coming from our products. So that would be 4 times the carbon-oxygen bond that comes from CO2. So that would be 4 times 799 plus 6 times our oxygen-hydrogen, which is 467. So if you plug that into the calculator, you'll get a change in enthalpy of reaction that is equal to minus 1267 kilojoules per mole. Now, if we compare that value to what we had from our previous problem where we were using enthalpy of formation values, we had a value that was negative 1367.5. So given the simplicity of this system, it actually gave a pretty close answer. There are some problems with it, which is why it's not completely reliable, and that is that the values that are in our average bond energy table are just that. They are average values. So our carbon-carbon single bond is an average of all the various types of molecules that have carbon-carbon single bonds. Now, what is attached to the carbon-carbon single bond can actually influence the strength of a carbon-carbon single bond. And so this value here will actually vary quite widely from that value depending on the individual system that you have. So for example, because this carbon here in our ethanol is bound to an oxygen, that will actually weaken our carbon-carbon single bond. And so the value for the energy of that bond is going to be slightly different than if instead of having an oxygen here, we had another carbon. The other problem is, as we had seen with our water, there was a difference between a gas phase and a liquid phase, and that had to do with the intermolecular forces holding that together. This particular system where we're looking at the bond energies does not include any account for intermolecular forces. So it works best when all of your components are in the gas phase so that you're not really having very strong intermolecular interactions. But it will give a very good approximation to the value that you're after. So what this would tell us is it would give us a good idea of the amount of energy that we can expect from our particular system, and then we can figure out what type of experimental setup we need to have to account for the amount of energy that we expect to come out of this system.